CAPTCHA. They are all things to copy and paste, and every single one of them is all full of non-printable characters that ruin it all in Unix. So they just make you cry. You have to like copy, retype every line, or you'll go out of your mind. That took me like a couple of days to figure out. So whoever wrote it in Visual or something. And every Microsoft product always changes all the characters to stuff that Unix keep. Some image of the war happened. Anyway, so we're at RSA. And of course, this is one of the most important protocols in the world. So we'll talk about it and how it works and some of its problems. So Diffie and Hellman published the public key paper in 1976, and that started the modern world of public key cryptography. There were rumors that the secret agencies had this for 20 years previously and kept it a military secret. But once the cat came out of the bag, everybody could use it. And this made it possible to communicate over an insecure channel without ever having a shared secret, which is like black magic. So that's transportation. And RSA is so expensive to use in terms of computer time that you almost never encrypt an entire message.
You do music?
Encrypt a private key and use private key encryption after that. That's the transport and the sign. And the other odd thing it's used for is digital signatures, of course. You take something like the hash of a message, which is also a short message, you encrypt it with RSA and send it, and you can encrypt it with your private key, so anybody can decrypt it with your public key and verify that it was really you. Assuming that they have some way to get an authentic public key for you, and that is one of the weak spots in the system. It doesn't address that because that's not math. There has to be some trusted repository of public keys. Anyway, the math is extremely simple. All you need to do is take things to a power and use modules. So X is the plain text, Y is the ciphertext, E is the encryption key. So you just take the plain text, turn it into a number somehow, then take X to the E mod N, and that is the ciphertext. And at the other end, they take the ciphertext Y to the D mod N to undo it. You remember back when we did modular arithmetic, we were talking about finding the multiplicative inverse. If you use one number to scramble something on a ring, there's often another decryption key where the same process will unscramble it. Let's see, somebody had something to say. Let's find out what it is. Can Tony mute his mic? All right. Now let me try muting everybody. That's good. I don't hear you, but maybe my sound is off. All right, that should do it. Good. Thank you. If anything is bugging you, let me know. Especially you remote people, I don't have any clue. You could be just staring at my nose all night and I wouldn't know. And that did happen at least once. Anyway, so key generation goes like this. The public key is these two numbers, N and E. That's what you want. And you make a private key of D, which you calculate, but you don't tell anybody. So you start by choosing two large primes, P and Q. You multiply them together, and that's N. Then you compute phi, which only you will know, P minus 1 times Q minus 1. And you get the private key D, so it's the multiplicative inverse of E on phi. And that will undo it. And that is kind of not obvious, but this can be done quickly. And so then you publish N and E to the world. You don't tell anybody P and Q, and therefore you don't tell anybody E. And anybody can encrypt stuff to you, and anybody can decrypt it. One thing not mentioned here is how you choose E. It turns out that you can safely choose E to be really small, like 3, and it's perfectly fine. If you make E small, then D gets bigger. As you might imagine, they have a multiplicative relationship here. But if you do that, encryption gets faster and decryption gets slower. And most people do choose a small E, so the encryption is easy. That's the game. So what's that?
If you choose a large E, then D gets smaller?
Yes, in principle. And that would make encryption slower and decryption faster. What's funny to me is I don't really know why there's this tradition of making encryption fast and decryption slow, because the most common use is you're a browser and you're going to be doing both operations. But in fact, you only do them once. So I guess it doesn't really matter. Because all you do is you do one encryption to send the private key to the server. Then it has your private key and then you never use it anymore. So I guess that's the point. This way your client machine can be weak and you put the burden on the server, which is logical, I suppose. Anyway, in Python, it's pretty easy. Go to crypto public key and import RSA. Then you can just call generate, and that will automatically find random numbers somewhere and make a p pair. I don't know how perfect the random numbers are. There are usually considerable angry people arguing about that. But it does do some kind of random generation. Then you have a public key, and you can now put in plain text of any length. And you can get the ciphertext this way. The ciphertext will be very long. I chose here to use a 2048-bit public key, which is what's currently recommended by the NSA for normal encryption. And that means that your output's going to be 2048 bits, even though your input is probably much shorter. It is automatically, it comes out that long regardless of the length of the input. I don't believe this automatically pads it, but we'll play with it more later as we go ahead. Anyway, you can decrypt it, of course, and then you get your message back out.
Sorry.
Yeah.
2048 is the N?
Yes, 2048 is the size of N. That's real important. So that means P and Q are actually 1024 bits. And when you multiply them together, the result is 2048 bits. And that's what's recommended now. 1024-bit RSA was recommended until a few years ago, and it still has not been cracked, but they've gotten up to like 768 bits. So they're close enough to it that they recommend moving up to 2048 or even higher now. So here's how slow it is. One key generation took 1/6 of a second, 400 encryptions took 26 milliseconds, and 5 decryptions took 0.013 seconds. So, you know, decryption is slow, encryption is really fast, and key generation is really slow, which will make sense when you see what you have to do to generate a key. It's bloody madness.
Can you go back over?
Yeah.
So we had 3 speeds for, what was that? Because you have more encryptions.
Yes, well, I adjusted that number to get reasonable numbers. So
one,
yeah, so you really could do 4,000 RSA encryptions in the time you take for one key generation.
and then you do 5 encryptions. And
Yeah.
it's small.
Yeah, that's right. It's probably better if I used 4,050 there to get them all to about the same size. But anyway, it's the generation is what's really slow. All right, so the setup phase is the key generation, and choosing the large primes is a problem. I mean, the whole point is these primes are so large that when you multiply them together, nobody can factor it. So that means the math has already gotten difficult. So how do you find a prime number 1,000 bits long? That turns out to be kind of nuts. All right. So here's an example of small numbers. If Alice's message is 4, Bob's over here. She's trying to talk to Bob. So this is the unfortunate thing. If you want to talk to Bob, the first person that has to do all the work is Bob. And so if you are somebody like a crypto expert and you want to send it to somebody who's not technical like a journalist, you're pretty much hosed because the journalist can't understand how to generate a key. And even though you know how, that doesn't do you any good. The person receiving the message has to generate a key. So Bob has to choose 2 prime numbers and then compute n, compute phi. Those numbers are 3 and 11. Phi is 3 minus 1 times 11 minus 1, so that's 2 times 10 for 20. Then he chooses E. Like I say, choosing E of 3 is fine. And now all he has to do is find the inverse of E mod 20. And that is 7, because 3 times 7 is 21, and that's 1 mod 20. So with this simple example, you can do it in your head. So now he has D, but he doesn't tell anybody. The public key is N and E, so it's 33 and 3, and all Alice has to do is take her message to the E mod N. So that take her message to the 3 mod 33, so that gives her 31. And at this end, what Bob has to do is take this mess to the D mod N. So they decrypt it by taking it to the 7th, and that's going to get it back to the original message. Because there is no division, the way you undo multiplication is by multiplying by the inverse. Yeah?
Is there any correlation between P being 3 and E also being 3?
P is 3, and what was the other thing? Is 3? E? No. P is usually huge, like 512 bits. E is often as small as 3. Another popular number is 65537. Relatively small numbers. But P and Q should be huge. Like these days, at least 1,024 bits.
And E just has to be a prime.
D,
E.
E. E has to be, technically, it doesn't really have to be a prime number, although all prime numbers are fine. It actually just has to be relatively prime to phi. But in practice, being a prime number would work. And the only numbers I've ever seen anybody really use are 6, 5, 5, 3, 7, and 3. But your bunch of numbers you could use, but it turns out that as far as anybody can tell, there is no reason to get fancy with E. Just the plain, ordinary, usual E is fine. All right. So it only does one arithmetic operation. Once you make the key, all you're doing is exponentiation, taking something to the D and taking something to the E. So the only thing you have to do is figure out how to exponentiate things fast. And they're going to be big numbers taking the big powers, so that is not a trivial problem. All right. And so any way you cut it, it is much, much slower than a symmetric encryption, like hundreds or thousands or tens of thousands of times slower. We did some speed tests last time I showed you. It's ridiculous. And that's why you really don't want to encrypt everything with RSA. You're totally wasting your time. All you want to do is send a private key and then use AES, which will be a lot cheaper. And as far as anybody can tell, just as secure. All right. So especially if you're going to do it on a power-constrained device like a cell phone, then you really want to not waste a lot of CPU doing anything sloppily. Now, you could try to do multiplication this way. So if you're going to take x to the e mod n, and e or d is something like 1024 bits long, then you're going to have x times x times x times x to the 1,024 multiplications if you do it this way. So this is completely impossible to do it because there's only, remember, even a 72-bit key is never been cracked by brute force. There's not enough computers in the universe to ever do 2 to the 1024 calculations of any sort, and there never will be. So you don't do it that way. This is just really stupid to do it that way. What you do is you use time memory trade-off. This is often the solution. Instead of just doing it one step at a time, you compute partial products that get you in the direction you want to go. So now x2 is x squared. You calculate the fourth by multiplying those two together, the 8 to the 16th, and you go down to 10 to the 24. And now I think you only need 10 rows to get down here. And now that you have these values, you just multiply them together. This is if you have a 1 in the 1024, next one if you have 5, 12, 256, and so on. So this way, you don't have to do a ridiculous number of multiplications to get to the end. In fact, it turns out that you have to do 1,536 multiplications to get any number this way, because you just square and square and square, and then save those and then multiply them. Yeah.
So when you're exchanging keys, the symmetric key, is it usually the sender or the receiver that's going to be deciding?
In principle, well, in principle, it could be done at either end, but in practice, remember that you have an RS. It has to be whoever put out the public key can only be receiving. So you'd have to go to that person unless you make your own key pair. And I think browsers do make their own key pair temporarily, but now I'm thinking about it, I wonder if that's not true. There's no reason for them to. All your browser would have to do is connect to the server, get a certificate, get a public key, then create a symmetric key and send that up. And I think that's all they do. That way you don't even have to generate a key pair at all on the client. All right, so that's the game. Even with square and multiply, this is still hard because those numbers you're squaring and multiplying are 1,024 bits long or so. So it's a big long mess. So here's tricks. A small e will make encryption faster. There's a thing called the Chinese remainder theorem that gets you a little bit of speed performance, but it's not enormous. It makes things about 4 times faster. And there's something called pre-computation, which sounds like another time memory trade-off, but they don't go into any more details in your book. And I'm not really that concerned about these. These are implementation ways to make it faster and save power, and I'm not very worried at that level for this class. So E, the one exciting thing is the E can be really small, like 3, and it's perfectly fine. You would think that something that small would create a weakness, but apparently it doesn't. So I said this makes it the fastest asymmetric scheme. It's not the fastest encryption scheme. The symmetric schemes are thousands of times faster, but it's the fastest asymmetric scheme if you make E small, because you shoved all the difficulty to the other end. All right, and here's the Chinese remainder theorem, which can somewhat accelerate exponentiation with that large value, but it's not simple to understand, and it doesn't really do anything enormous. Remember, quantum computing makes an incredible difference. If they get that working, that's going to destroy this whole system. to where you'd have to have keys of something like 1 million bytes long to have security. So this is cahoots. And here, and here, and here. That's not right. Back, there's no back. It's play, that's what I want. Not that one. All right, one more time. That thing keeps coming down and getting in my way. Anyway, that's the one I want. Play. All right. There you go. They changed their music for Halloween. So. All right, wait a few more seconds and see who else I got. All right, looks like no more are coming. Oh, there comes somebody. Okay. All right, in a few more seconds, I'm going. Looks like that's it. Okay. Questions? All right, what's in the public key? All right, that's N and E. N is the large number. That's the public key that has 2048 bits or so, and E is that other number that can be really small and it doesn't matter. And, you know, in principle, you could use any letter to mean anything, but in practice, everybody sticks with these standard letters, which I think come from the original paper. Just like everybody always uses Alice and Bob. All right. So which one of these has to be a secret? All right, and P, good. P and Q are your prime numbers. You have to keep them secret or they ruin the whole thing. All right. What's the slowest operation? All right, key generation, of course, by far the slowest because it has to guess for those prime numbers. Which number is made short? All right, E is small, that's right. Okay, what's fin? Which they write as phi of n. That's what it is. What this actually is, it's the number of values you can use of the space. You can't use all n. You can only use this many values because you can't reach all the n's by generating the periodic multiplication. You can only reach this many. Anyway, that's fin. And it's that's what you need to create the private key. It's, again, a number that only the key generator will know. You never let anybody have this number either. All right. So it's R. Dugan. I know him. And Tony, I think I know who that is. And Anna, I might be able to figure out who that is too. All right, so let's see, back to here. All right, so the finding large primes turns out to be kind of insane. It turns out the only reasonable way to do it is to just guess. Take random numbers and then test to see if they're prime. Now, at first, I thought this would be impossible because I thought there wouldn't be very many prime numbers, but it turns out that there are actually quite a lot of prime numbers up there. You can see, here's how common primes are. This is, I think, the gamma function or the zeta function. Anyway, it's 2 over the log of p. So it turns out that in the range of 512 bits, about one number out of every 177 is prime. So you really don't have to guess too many times before you'll just get lucky and find a prime number. Yeah.
Isn't there like a higher probability if you have 2 to the n plus 1 that'll be prime?
Oh, yes. That's a very good point. Those are like the RSA primes or something, 2 to the n plus 1. And of course, you don't want to use them because they're predictable.
Okay.
That's the problem. Oh, there are certain prime numbers that get really large and are easy to find. But if you use them, then an attacker will find them. This is like using a password that's a commonly known password.
Okay, I always wondered that.
Yeah, so the system relies on you using really random prime numbers, and that turns out to be a huge problem, of course, in practice, because there are almost no random number generators that really work. They're all usually very imperfect at being random.
There's no any algorithm or anything to find it?
No, there's no algorithm to find prime numbers, and there's no algorithm to create randomness. Both of these are difficult problems. The best way to create randomness is to magnify Johnson noise to a resistor. Try to find a physical process that's random and magnified. And there's no algorithm to find general prime numbers. There's just certain categories of prime numbers, like he was saying, the RSA primes or something that you can find. Yeah.
But are there algorithms to test?
There are, but only probabilistic ones. That's why,
Really?
yeah, the whole thing I thought was kind of nuts. The only real test for a prime number is to try dividing it by every number up to its square root and make sure that none of them divided evenly. What's that?
That's brute force.
That's brute force. And that's the way to be sure. But there are probabilistic tests that give you perhaps a 50% chance to detect if things are prime. And then you run it for 100 times. It's nuts, but that's the way you really do it. There's the Fermat test and the Miller-Rabin test. And these are just mathematical tests that will detect with some probability if a number is not prime. The original Fermat one only does it with 50%, so you run it 100 times. The Miller-Rabin is actually faster, but when I did this, I did it in the 70s when this stuff was all brand new, and the only thing we had was the Fermat test, and it was just kind of nuts. You have to guess up to 200 times or more to get a prime number, and then each one of them, you have to test about 100 times before you believe it's prime. That's why it's taking so long to make your keys.
So
It's doing all that junk. Yeah.
when you're generating a key, it's doing these calculations?
Yes, it has to take 2 prime numbers, and each one of them will take hundreds of guesses, and each guess will take hundreds of tests. Although really, to be fair, if it's not prime, it'll fail pretty soon. 50% chance, another 50% chance, probably within 5 or 6 tests, it'll fail. And then you go on to the next one. But the one you like, you really put through a whole lot of tests to be highly confident that it's prime.
But you always test if it's not prime.
Right, that's all you're testing. If something has a chance of, and you know, if you find out that it's not prime, you're sure of that. But if it doesn't find it's not prime, that doesn't prove it's prime. So you have to keep feeding it other random numbers and guessing against them. So here's the test. And the test has a random number in it. So you choose a random number, and then you do some math on that random number. And with a certain probability, non-prime numbers will have a known result here, and prime numbers will not. So then you choose a different random number, do it again, and S is your security factor. And it turns out that you don't have to do so many Miller-Rabin tests. Maybe up and late around 600, 3 or 5 cycles of that is good enough. So from the looks of this, I guess the test becomes more accurate for longer numbers. Anyway, that's the game. You guess numbers. All right. So that's RSA. Now there's a couple of problems here. RSA is deterministic. This is what we talked about as textbook RSA, where you take the input data and you turn it into a number, and then you raise that number to a power. Therefore, if you have another message that's exactly the same, you'll get exactly the same output. Now, this is really bad for things like network traffic, because network traffic is all full of ARPs, and the ARPs are all the same, and you know what they look like, and they're easy to spot. So That's really bad. The user can guess the plain text. There's also some plain text values that don't encrypt worth a damn, like 0, 1, and -1. And what's even worse is RSA is malleable. I don't know if I have a chance to put this in this class, but forging digital signatures is bloody awesome. See, suppose I want to modify something without being able to read it. Like suppose you're encrypting a dollar amount, and you're taking X to the E, but I want to double the dollar amount. Well, I can create the encryption by just calculating together a couple values. I can multiply it by more things and modify it without understanding it. And I'm not going to go into that in detail tonight, but I am going to show you a similar attack against AES, the padding oracle, after we're done with this. There are cases, and you get a lot of these in the Web Application Hacker's Handbook, where you can take encrypted stuff and figure out how to modify it so it will have a useful meaning, even though you can't decrypt it. And RSA has that problem. It's malleable. So you can, here you can calculate S to the E. So since I know E, if I want to double a dollar amount, all I have to do is take the Y and multiply it by S to the E, which I can figure out. So I can multiply the dollar amount by S. And it'll decrypt to that, and the other person won't know what happened. So that's why textbook RSA is not really that good. It falls to these trivial attacks. So what you do is you pad it. And remember, you have this huge input buffer, because you're going to end up with 2048 bits or something, and the message is almost always very small. So you pad it before the message. You put in a seed mask and a hash value and a couple other things here. So it's actually got an integrity control inside there. And then you encrypt this whole mess. So when you decrypt it, you take the message and compare it to the hash. And now that's very difficult for anybody to forge. That's how you solve it. That's PKCS number 1. We're going to use PKCS number 7 a little later tonight with the padding oracle attack. There's various recommended ways of padding. This is how you're supposed to pad RSA. All right, so that removes all these problems. It's no longer deterministic because you put in a seed, and the seed is different every time. So if you have identical input, you will not have identical output. It's no longer got any problem with numbers like 1, 0, and -1 because you've added extra stuff to the front that is not 1, 0, or -1, so you're never actually encrypting the value like that. And it's no longer malleable. I can't just take your number and multiply it by a constant to create a valid encrypted other number, because multiplying the hash by a constant will not result in a valid hash. So it does fix all those problems, and that's how it's actually used. All right.
Sorry.
Yeah.
If I understood this correctly, if the message is like this size, I need to pad
Yes.
so the total of 1024 or 2048.
Yes, bits. Yeah, so if you actually want to encrypt a really large message, like you're using PGP that encrypts a whole email, then you will have blocks, and you'll have some issue of how to pad the blocks. And I looked it up, and I haven't found any good statements about how to do that. That's a very rare application. Most of the time, the only thing you're trying to send is an AES key, and it's only 128 bits long. So the most common situation is the one I'm talking about, where your message is much smaller than the block. But you're right. If you were trying to encrypt a large message by cutting it into blocks, then I guess you'd have to consider those methods we talked about before, like cipher block chaining or something. And there probably are some writings about that. But when I hear people ask, I looked up this question earlier today, and most of the people I saw said, you don't get it. You'd never do that. You just send an AES key. You'd never send a long message of straight public key encryption. It would just be masochism. And it kind of is. But I know PGP actually works that way. Or at least I was under the impression it does, but maybe it doesn't. Maybe it actually mixes two encryption routines. It certainly is possible mathematically to do it that way. But I don't know any cases where it's really done. So here's the weaknesses. These are the attacks. You can do protocol attacks, mathematical attacks, and side channel attacks. Now the protocol attacks will be attacking the design of it from design flaws. And as we said, malleability is a problem. If you use textbook RSA without padding, then people could create valid ciphertext without the key and trick you. So that's what the padding does. The padding with this integrity check makes that essentially impossible. Then there's mathematical attacks, right? If you can find some way to do the math, and that is the whole point of it, it is designed to make this difficult. The only mathematical attack that is known is to somehow factor n into p and q, and there are a whole bunch of people out there trying to find the smartest way to factor numbers, but so far, none of them have found a way that really is fast enough, although they keep getting better. And I think I got a graph here Yeah, I took the numbers from I could find online, the numbers from your book, and I put them in a graph from 1990, 2000, 2010. Here we are, 2017. You know, they keep getting a little faster and faster. So I just had Excel put a line in it, and you can wonder. That's why, as you can see, everybody's been using 1024, and they've started telling us you better knock off using 1024 because it really doesn't look impossible. The 1024 is going to get it. And so 2048 will last for a while. That's off the top of this graph. Except quantum computers will probably mess up this curve if they really come out. You know, predicting the future is pretty dangerous. All right, then side channels are really bad. This is where you mess up your math because somebody has information that they weren't supposed to have in the math. Like they can watch the power consumption or the radio emitted by the wires or otherwise get information about the key. And that's pretty gruesome. Power consumption is a pretty big one because square and multiply takes a lot of power. So if you square and then you multiply because the key bit is 1, that's 2 bursts of power consumption. And if you square and the key bit is 0, then it's 1. So you can just look at the power profile and it traces out the key 0, 1, 1, 0, 1, which is pretty awesome. And there's a similar channel is timing channels. If you take how long it takes to combine to do different kinds of encryption, it'll take longer when the key is all 1 than when the key is all 0s. And so you get some information that way. And these things are actually very hard to get to the bottom of.
So
yeah.
Where would you be tracing the power from?
Well, you could, in principle, do it from the wall socket. You could do it from the radio emitted by the transformer in this thing here, the power generator. You could put some kind of malicious app on the device that's monitoring the power. It could be a lot of ways.
So it needs to be close to the physical device that's...
Yes, I would say so. You have to be at least on the same circuit as the physical device. And if they're in a complicated building, you'd have to be closer to that if there's many devices on the same circuit. But if you can do something like get a server to run late at night when nothing else is happening, you might, I suppose, be able to do it by monitoring all the power going to a floor or something. But how practical these things are, I don't know anybody that's actually tested real practical versions of it. The one I've seen is radio emissions. A group in a foreign European country did this. They did it about 100 yards away through wooden walls with an antenna 6 feet across. They could see every key you were typing from the radio emitted from the wires in the keyboard. So, you know, the Tempest project did this decades ago, back when there were CRT monitors, and they said it is scary as hell. They can see everything on your screen. They can see everything you type. They can see what the computer is doing from far away by the radio it emits. So you really have to work in a cave with metal all around you if you don't want that happening. Yeah.
I've seen that with smart cards, but you hang the scope probe sampling scope on the rail of the DC supply.
Right.
Much easier. I don't know how you would be doing that.
Yeah, it would be an issue, but I bet you could do it. Yeah.
Because you're having to go through AC to DC conversion.
That's right.
And you have less metrics to be.
Yeah. Yeah, you're right. It would be much more difficult out there.
Yeah.
All right. So that's the game. So one option you could do is you could just make an algorithm that wastes time by always doing the multiplication whether it has to or not. This is often also the solution for timing attacks. Never write efficient code. Always make sure to waste time so it always takes the maximum time to do everything. The opposite of what they train you to do in programming would be more secure. And then there's fault injection. The issue here, this was a powerful attack in 2010. They got a 1024-bit key by lowering the power supply to where the processor started making mistakes. And the point was, that was how they created an artificial situation to study this. But what they said was real processors make mistakes because of cosmic rays and because of thermal degradation of the RAM. So if you do millions and billions of RSA encryptions that are all supposed to be the same, then some of them are off by a bit because one bit gets dropped during calculation, and that has a non-random effect on the result. So that by getting, I think, 170 defective computations, that was enough to totally discover the key. Because they went through the algorithm and figured out where the errors are going to be and what result it will have. And they could deduce the key from that. So that was the plan. That's another side channel attack. Just because you're implementing it in real computers, there's an unexpected pattern in the output that leaks the key. All right. Well, you know, it looks to me like we can probably do the cahoots. They only take 20 seconds each, and I got 5 minutes. Maybe it's time for me to pay for the other system, but I haven't done it yet. All right. So I'm going to come back after this and do the Oracle attack, because that's awesome. I was very happy when I got it working. But we'll take a 10-minute break after the cahoots before that. So 596, 026, there they come. I don't see how these people are making any money, but it's a nice product, this Kahoot thing. I don't see any ads. You don't see any ads, do you? I don't know how they're making money, but I do have an ad blocker. You're right. That might be it. Anyway, I'll wait another 5 or 6 seconds. All right. 4 questions. To make a 2048-bit public key, how large do P and Q have to be? All right. Yep. Half as much. 1024 each. All right. 1024 is the answer.
Yeah.
Yeah.
Well, I had 2 answers. I didn't notice that. Oh, well. Anyway, there should have only been 1. So how many guesses will it take to find a prime number 512 bits long? $200? Yep, they're pretty thick on the ground, really. All right, what prevents repeated input from resulting in repeated output? All right, that's the padding. Good. All right, and what's the most effective attack against fully modern RSA? Side channel is the only thing that works. None of the rest of these, you have defenses against all the rest of these. Padding Oracle doesn't apply, and these 2, you've got defenses built in, but the side channel keeps on happening. All right, Buster, and password, and Artyom. All right, and I'm going to take a 10-minute break, and then at 7, we'll come back and do the Padding Oracle.